You ready to go?
I also click this recording button.
Okay, so take it away.
Cool. All right, thanks everyone, and thanks for the organisers for inviting me and letting me speak about this hopefully interesting work that we've been doing at Manchester. So it's called Numerically Exact Quantum Work Statistics. I'm just going to break the title down to start with. So what do I mean by work? Basically, the energy that it costs to perform a useful operation or to control something. Quantum work then is going to be, let's imagine I've got a quantum system that I can control and I want to perform a useful operation on that. What's the energy that it costs me to do that?
Can you speak up?
Can I speak up?
There are mics over there.
Is this better? So we don't want to do that. Okay, is that okay? Yep, good. Okay, so the word statistics shows up in the title because if you were to perform the same operation on a quantum system over and over again, you would see that it costs a slightly different amount of energy each time. And one of the things to keep in mind is that this quantum system is open, it's interacting with an external environment, and basically that environment interaction is going to cause bad things to happen to your system. So here's your quantum system, and there's a bunch of stuff interacting with it from outside, and then maybe something happens to your algorithm that you don't want to happen. So if you want to simulate what that environment might be doing to your system, especially in the context of work statistics, you might be inclined to perform some approximation about the system-environment interaction, like the Markovian or the weak coupling approximation. And if we were going to do that, then the title of my work would be Approximate Quantum Work Statistics. But instead, we're going to take the full environment into account, no approximations, and we're going to get numerically exact quantum work statistics. So our goal then is to calculate these statistics with no approximations on the system-environment interaction. Okay. So I'll do a quick aside on the dynamics of an open quantum system. So let's say I've got some composite system environment density operator at time 0, and I want to evolve it through time and get some final state. It's going to evolve unitarily like this, and I'm going to call it made up of two things. One which I'm going to call forward time propagation. And the reason I use this language is because if you look at what U does to an initial state, it moves it forward in time. And then it's also made up of this, what I'm going to call backward time propagation, just U dagger. And I call this backward because if you apply U dagger to a state, it's going to evolve it back in time. Now, another way of writing this is just some unitary evolution on the composite state. And basically, we don't usually care about what happens to the bath, we just care about what happens to the system. So we trace the bath out, and that lets us use this Costa decomposition. And then we can write this as an influence functional acting on our system state. And in between adjacent legs of this influence functional, we have these M operators which are local on the system. Now this influence functional tells you how the environment influences the system, and it's made up of the environment and the interaction terms in the Hamiltonian. And then these M operators are due to the system Hamiltonian themselves. So we can encode this influence functional as a process tensor, and then basically this process tensor is very high rank, so it's pretty much impossible to actually calculate this thing. But you can use tensor network compression techniques and get this in what's called matrix product operator form. So this thing right here is a numerically exact way of calculating how the system state evolves in time, taking the environment's influence on the system into account exactly, so no approximations. So we've gone from a high rank tensor, which was the influence functional or the process tensor, to a product of low rank tensors, which are these Q things. And they're connected by these inner bonds, which are these sort of red lines going between the Q. And these red lines are these inner bonds, and essentially what they're going to do is, if I get my laser pointer up, no, okay, never mind. They're going to allow the flow of information through time, so it's going to allow for non-Markovian effects to be captured. Right, why would we bother with any of this? This unitary evolution is intractable, you can't calculate it because the environment usually lives in an infinite dimensional Hilbert space. This matrix product operator form is both tractable, and it converges, by which I mean if you give me enough computing power and time, you can get it to give the exact same answer that the unitary evolution would. Right, why am I talking about state propagation? basically because work statistics and state propagation are very intricately linked, which I'll show you now. But first of all, what do I even mean by work? So here's my open quantum system, and I want to drive this system, I want to control it, I want to do work on it. And I ask, how much is this costing me? So one way that we can use to define and calculate work is the two-point measurement protocol. So I'll show you what this means now. The first thing we do is we somehow perform a projective energy measurement onto the composite Hamiltonian, so the system and the bath and their interaction. And I get some outcome E0. I then let the full thing evolve unitarily, so I continue driving my system and I otherwise just leave the full thing alone to evolve. And then some time t later I perform a second projective measurement and I get some, one of the eigenvalues of h of t, et. You can then define work as the difference between these two measurement outcomes, but because they were both projective measurement outcomes, they're stochastic, so this definition of work is probabilistic. You need to define it through a probability distribution. So you basically just repeat that experiment over and over again, get a different value of work out each time, and then you can build up some probability distribution. So this tells me if I did a specific protocol that took a time t, what are the possible values of work that it cost me, and what are the associated probabilities that they occur with. So this is the main thing that we want, but as with a lot of things, it's actually much easier to just work with this thing's Fourier transform, which is called the characteristic function. So this is a complex valued function of some parameter chi. Chi is the conjugate to work. So chi is to work what energy is to time, or frequency is to time, what position is to momentum. So they're just like Fourier, they're related by the Fourier transform, basically. Now this thing, you can write it in a really cool and interesting form, which is just, it's the trace of this thing called a generalized density operator. So it's the density operator of the system and the environment that's just been modified by this parameter chi in some way. And we'll see how it's modified here. And this expression isn't too important, but I'm just going to basically show you where these things come from the two-point measurement protocol. So we start off with our initial state in the middle, rho 0. My first measurement gives me this term. The unitary evolution gives me these terms, and the second measurement gives me this term here. Now, maybe a more intuitive way of thinking about it is thinking about it visually. So we start off with rho 0, and we know that we need to evolve it in time because rho of chi and t depends on time, of course. And we know that we need this unitary evolution, which we saw a few slides ago before. And then on top of that, it also needs to be propagated in what I'm going to call the chi direction. Chi, we call this counting parameter because it helps us count work. So I need to move somewhere in this, on this set of axes. And the question is where? So we interpret this term which acts on the initial state to move us upwards in this diagram. It moves us forwards in the chi direction. We then have unitary evolution, which moves us forwards and backwards in time. And then we have this final term, which is the second measurement, which moves us backwards in the chi direction. And if we do this, we end up with this generalized density operator. And remember, this thing encodes the work statistics. So the issue here is, it's not obvious how we actually perform this evolution using this Trotter decomposition that we need to use. So what we do, and this is the most important thing about this work, is we map these two axes onto a new axis, which we call the generalized time axis. So I just rewrite everything in terms of tau. And now I just have a unitary evolution, or a sort of unitary evolution on my initial state, which gives me my generalized density operator, which again encodes all of these statistics that we care about. So let's just see how these two things are similar. Basically, all I need you to do here is just look at these diagrams and see that they look quite similar. Right? There's a few slight differences, but the details are not too important. They basically are just propagation along some axis. One is time, one is what we call generalized time. So here's our propagation, which gives us our statistics, and we can just say, well, this is kind of like that unitary evolution that we had before. So Trotter decomposition now makes sense. It makes sense along the generalized time axis, but it didn't make sense when we had to propagate along t and chi. So again, we just trace out our environment, and now we get this influence functional again, which is exactly the same as it was before. And the only difference gets encoded into these n propagators, which, as I said, are local. They just act on the system. They're really easy to calculate. And the difference that appears here is quite trivial compared to the propagators that we had before. So what I mean here again is this is our state propagation, this is our work statistics. And once again, just look at the diagrams, they look very similar. Right? The colours are a little bit different. The influence functional is exactly the same. The only difference is in these operators, and the only difference in these operators really is I have to define what I call a forward and a backward tau-dependent system Hamiltonian. And this difference is fairly trivial. It's literally like 6 lines of code. If you can code up a time-dependent system Hamiltonian, we can very easily give you a tau-dependent forward and backward system Hamiltonian, and then you get your work statistics. Okay, so once again, we just perform our tensor network compression and get this in matrix product operator form. And this is now something that you can actually perform on your computer. And I should mention that all of this, right, we use this thing called time-evolving matrix product operator. It's a particular way of simulating the bath. Most of this, well, all of the mapping onto the generalized time axis is not dependent on this matrix product operator thing. So you can simulate the bath in any way that you want. Okay, so I'm aware that most people, well, some people might not have understood anything I said because maybe the explanation is too fast. So I've just got 2 lines which tell us pretty much everything we need to know. So we can track this generalized density operator, rho s of tau, using a process tensor. So a numerically exact way of tracking the state. Take the trace of it and you get this characteristic function. If you have this characteristic function and you Fourier transform it, you get the probability distribution, you get your work statistics. So in that way, you've now got numerically exact work statistics. Okay, so now we apply it to a specific example, which is Landauer erasure. So the question that we want to ask is, how much energy does it cost to erase the information in a qubit? So here's our qubit, excited in ground states and surrounded by some environment. It's got some population in the excited state, and we specifically started off in the mixed state tensor product with the thermal environment, and we want to drive our system, force it into the ground state, and we don't care what happens to the bath. Right, so the specific protocol looks like this. We've got some sharply peaked spectral density. We start off with our 2-level system very far detuned from this peak, so it doesn't want to interact with the bath here. There should be minimum dissipation. And then we move it into resonance. So we change the splitting of the 2-level system so that it now wants to interact with the bath. There should be maximum dissipation here. This is where we should erase our information. And then we just make the process cyclic by changing that detuning back to its original value. Okay, so if we care about erasure, we probably care about how well that erasure is performed. So what's the fidelity with getting your system to the ground state? So here we plot that for a bunch of different coupling strengths, alpha, and then on the x-axis, I'm basically showing how fast do I change that energy splitting. So do I do it really quickly or do I do it really slowly? And we see some interesting things. Well, maybe not that they're not too interesting. I think they're quite obvious, actually. The slower you do it, the better the erasure. The stronger the coupling to the bath, the better the erasure. Now, one interesting thing that you can do with process tensors is just very easily change the Hamiltonian. So here we add a shortcut to adiabaticity in, and you see some interesting stuff here, which is basically the shortcut makes your erasure much better. And it also works even better for even stronger couplings to the bath. So here we just show zoom in, and you can see that there's pretty drastic increases in the fidelity when you're using the shortcut compared to when you're using the bare Hamiltonian. So here we show the work the work mean and variance, so the low order moments. And basically the reason that I'm showing this is just to show that, okay, we see quite big differences at very short protocol times on the left-hand side of the graph. But as your protocol gets slower, as you get more adiabatic, there isn't much difference between what the shortcut is doing. Even though, if we look back at the fidelity, there's still very big differences in the fidelity when using the shortcut. So the problem here is that the improvement in erasure is not being captured by these low order moments. So that leads us to calculate the full distribution. And specifically, we look at these points here on the next slide. Okay, so this is a numerically exact work probability distribution for this protocol. It looks like this. And then if I zoom in, you can't really see, but I'm zooming in on those 3 peaks there. And we have certain closed system transitions. So these ones in the top right-hand corner in the inset are possible without the bath. And then on the right-hand side, this dissipation-induced erasure is due to the interaction with the bath. So once again, we can just easily add in a shortcut to adiabaticity, and the main shape of the distribution doesn't change. But what happens is you see those 2 peaks, which I've labeled excited to ground and ground to excited states, they get reduced down to 0. So this appears to be what has caused that increase in fidelity, but hasn't shown up in the mean or the variance. And then another thing we can do, because like I said, we've made no approximations in any of this work. So not only have I not made any approximations about the bath, we also made no approximations about how quickly we can drive our system. So we can show very non-adiabatic probability distribution as well. Now these oscillations, if anyone has any intuition about what they are, I'd quite like to know, please, because we have no idea what they are. We're fairly certain that it's not due to the Fourier transform. Like, we've tested everything we can think of, and we're pretty sure it's not due to the Fourier transform. So we think they are physical oscillations, but we just have no idea why. Because there seems to be there's certain values of work that are being favoured over others, right? Like the peaks of these oscillations are being favoured, and we just don't know why. And again, we just show the shortcut applied to this faster protocol here. And so what has all this told us about this shortcut? Well, it improves the erasure fidelity. There isn't obvious reasons in the low order moments why. So when we look at the full distribution, we see that those peaks corresponding to closed system transitions got suppressed. So therefore, knowing the full distribution gives us more physical intuition into what that shortcut is doing. Right, so what's new in any of this work? You can now get full counting statistics for work transfer for open systems which are strongly coupled to non-Markovian environments, so that's nice. You can have non-adiabatic or very fast driving. I think that's also quite nice. It's very easy to change the system Hamiltonian, which if you're interested in controlling an open quantum system, I think that's probably quite important to do. You can change your system Hamiltonian slightly and look at what that does to the full distribution of work transfer. And then finally, I mentioned this earlier, but this technique is applicable to any open quantum system. You're not limited to this matrix product operator form of simulating the bath that we showed. So I'd like to thank my collaborators at Manchester, Sheffield, Heriot-Watt and Dortmund, and then various funding sources, and say thank you to everyone. Also, there's no paper out yet. It's coming out in a week or 2. I also put videos online on YouTube, so you can watch them if you're interested. The code will also be put out when the paper is out. You can reach out to me personally on my email, or you can just talk to me at the conference. So, thanks everyone.
Thanks, Mike. That was a really clear, interesting talk. Do we have questions? Yeah.
Couple quick, you may have mentioned this in your model with the Landauer ratio. What is that?
Sorry, what do you mean?
Oh, sorry. What's the environment? Because the system is just a 2-state system. What's the environment?
The environment is just like a collection of bosons.
Collection?
Bosons.
Oh, okay.
Yeah.
Okay. And then, so when you use the shortcuts, are these shortcuts calculated assuming unitary evolution?
Yes, they're assuming the closed evolution. Yeah,
Okay.
yeah,
Okay.
yeah. And sorry, I should have mentioned what the shortcut was. It's essentially an instant turn on and turn off of this term at the end, this sigma dot over 2, theta dot over 2 sigma y. So that is possibly the cause of these oscillations in our distribution. But again, we're not too sure.
Instant, you mean just kind of impulsive at the end? Very strong?
I just mean that after t0, I turn it on and it's on, and then right before the final time, I turn it off. Yeah.
Thanks.
Yeah, thanks for the nice talk. So like you say it's numerically exact, but that's probably because we know the spin boson model is exact instance function, right? Like
Yes.
for a generic bath, I don't expect that. Like you could need exponential bond dimension for it to be. Like, do you have an idea of how well we need to scale the bond dimension of the MPO to get the distribution to converge?
Perfect. Yeah. So Eric and Moritz worked on this thing called ACE. I don't know if you've heard of that, Automated Compression of Environments.
Oh.
So this is like a numerically exact way of, as far as I'm aware, simulating any bath. So they've told me that if you can get ACE to converge, then this works with any bath. That is quite a numerically difficult thing to do, to get it to converge for any bath, but it is in principle possible. Yeah, thanks.
Yeah, the question is related to that. How does the one dimension depend on the drive you're using? Because it should, the correlations you're tracking, right, should depend on how fast you drive the system, what controls you use.
As far as I'm aware, the process tensor does not depend on the system Hamiltonian. So I don't think the... Sorry, I had way too many slides, didn't I? As far as I'm aware, the influence functional, yeah, it doesn't depend on the system Hamiltonian. So I don't think it will depend on how fast you drive.
But so you make somewhere you make an approximation, right? I mean, when you model your, or when you try to simulate your open systems through matrix product state or tensor network in general. And I'm wondering how that approximation is influenced by the spectral density, say, of the bar, coupling, weak or strong, and the drive.
So I'll be honest, I'm not sure what you mean by the drive.
Sure, Hamiltonian.
Yeah. I'm sorry, I'm still not sure. Maybe we could talk afterwards. Just off the top of my head, I'm not entirely sure what it is that you're asking. Okay, thanks.
Sir, if I could rephrase what he's saying, I
Yeah.
think like you could have maybe a low bond dimension and then like still get some properties if they're like not, if those properties don't require the low lines of modes of your influence function. But I guess what he's saying is if you require those properties in some way that because of what your drive is, then the thing that you want to compute might depend on the drive specific thing.
Yeah, maybe we could talk afterwards because
Yeah.
off the top of my head, I'm not too sure exactly what it is that we're trying to talk about here. But thanks.
Thank you.
Let me just ask this because I wanted to know the introduction of this kind of pi parameter, is
Yes.
this related to like kind of tilted booleans and like counting fields and all that kind of thing?
Yeah, so what I call the counting parameter, people call the counting field. Yeah, it's the same thing. Yeah.
Okay, so let's just type
Nice one.
Mike again. Thanks very much.